section 1.3. Oops. So let's start section 1.3. Section 1.3 is on lines. So first, draw some line in the plane. And now let's do it relative to the x and y, to some x and y axis. So to some coordinate system. Let me assume that once I set this coordinate system, that this line is not vertical in this coordinate system, meaning that the line L is not parallel nor coincident with the y-axis. Then we have the following property. If I take a point on the line and move 1 unit in the to the right, then I can do either a fixed number of units up or down to get to another point on the line. And we can do this for any line that's not vertical. We can somehow eventually get to another point on the line. And suppose that that distance here is m to get to another point on the line. If we go up, I'll let m be greater than 0. If I go down to get to another point of the line, I'll let m be negative. We will call m the slope of my line. It turns out that for any line, if you pick any point on the line, then the slope will always be the same for any fixed line. And you can see that, well, we'll see that in the future by scaling. You could also do similar triangles. So let me recall terminology and some notation for the slope of a line. So again, let L be some non-vertical line relative to some coordinate system. Then the slope of the line is just the race over the run. It is the vertical change over the horizontal change. So vertical change over horizontal change. It's the change in y over the change in x. It is, well, the change in y, we call that delta y. Over the change in x, which we call it. And so the change in y over the change in x, delta y over delta x. It is, well, the change in y, so y2 minus y1 over the change in x, x2 minus x1. And so the slope is just y2 minus y1 over x2 minus x1. So long as x1 is not equal to x2, you can always choose a point on the line such that x1 is not equal to x2, so long as this is not a vertical line. Note, the slope of a vertical line is undefined. The slope of a horizontal line is 0. Sometimes, in some classes, we say that we define the slope of a vertical line to be positive infinity. Let me do on page 31, problem number 14. And so, in problems 13 through 16, find the slope of the line and interpret the slope. Okay, so let's do that. So first, let's find the slope of the line. Well, I guess I picked x1s and y1s. And so, that makes it life easier. So the slope of a line, well, through 2 points. on the line, x1, y1, 2y2. And so the slope is just equal to y2 minus y1 over x2 minus x1. So in this case, the slope is y2, 1, minus y1, 0, over x1, x2, negative 2, minus x1, 0. It really doesn't matter which one you take as the first point and the second point. But in this case, it's easier because you're just subtracting 0. And so the slope is equal to 1 minus 0 is just 1, negative 2 minus 0 is negative 2. So slope is a negative 1/2. So now, let's interpret the slope. So in this case, what it says is, well, if you go 1 unit in this direction, you go down, negative 1/2 units, or you go down, 1/2 unit, or maybe I could say this is the rise of the run, so I can make that a maybe I'll make this, I'll write this as a negative 1/2. I'll make this the rise, negative 1, and the run 2. So it'll make the interpretation a little easier. So if a point, or if P is a point on the line, then there is a point, there is another point, Q on the line. I guess I need another page. Two units. Two units. There, spelled correctly. To the right. P. And 1 unit from P. So that's the interpretation of the slope. Any questions about that? Okay. Let me do problem number 18. In problems 17 through 24, plot each pair of points and determine the slope of the line containing the points. Graph the line. So, determine the slope of the line through points x1, y1, x2, y2. So that's y2 minus y1 over x2 minus x1. And I don't really care. I guess I'll call this x1, y1, and I'll call this y1. I'll call this x2, y2. And so the slope is equal to y2 minus y1 over x2 minus x1. And so I get the slope is equal to 2 over negative 1. Therefore, my slope is negative 2. Okay. So now it says that I should graph this. Let's do it here. Let's see, the point is 4, 2, and 3, 4. Okay. That's right. Sorry, 4. 1 over 2. So I have the point 4 and 2, 3, and 4. Okay, so the line looks something like this. So I have here the point 3, 4 and the point 4, 2. So you notice if I go over 1, oops, if I have a run of 1, I have a rise of negative 2. So yes, that looks correct. So yes, that seems to be a correct slope. Okay. Equations of a line. So this is just recollection of the equations of a line. So we have several equations of lines that are popular. The general form for the equation of a line, ax plus by plus c equals 0, is called the general equation for the general form for the equation of a line. So note that every line in the plane can be put into this form. So if I have any line in the plane, I can write it in the general form. However, this form is not unique. Notice that if you multiply everything by both sides of my equation by a non-zero constant, then you have a different form, but it obviously is still the same line. All you've done is multiply by a constant. So we usually try to write them, the general form, in a standard way so that there's a unique answer for the line. Obviously, not every line can be, I can't do that for every line, but for problems that you have in the homework set or on exams, you can put them in this form. So if A, B, and C are integers, and if A is greater than 0, and if A, B, and C are relatively prime, meaning that the greatest common factor between A and B and C is just 1, then this is the preferred form that we like to write our general form in. This is the form that you would write on an exam, on the homework set. It is the form that you would see if you look at the answers in the back of the book. That's how they would give it. So when would you use the general form for the equation of a line? Well, you would use it when you determine distances to a line. So let's just recall the formula for the distance from a point to a line. So the distance from the line ax plus by plus c equaling 0 to the point x0, y0 is given by the following formula. The distance is equal to, well, just replace x0, x and y by x0 and y0. So it's a x0 plus by0 plus c. Now, it's a distance, so it has to be positive, so or non-negative. So you better put an absolute value there just to be sure that you don't get a negative value. So put the absolute value over the square root of, well, a squared plus b squared. And that's the distance from any point in the plane to a line in the same plane. So the standard form for the equation of a line, very similar to the general form. It is just ax plus by equals c. Now, just like in the general form, every line in the plane can be put into the standard form. But again, if you multiply both sides of the equation by a non-zero constant, it's still the same line, but it has a different standard form. So in general, there's an infinite number of equivalent standard forms for any line. So if you can rewrite it in this preferred form, then we like that it's in the preferred form. So assume that A, B, and C are integer valued. Suppose that A is greater than 0, or greater than or equal to 0. Yes, good. And suppose that A, B, and C are relatively prime, so that the greatest common factor between A, B, and C is 1. Then we say that this is the preferred standard form. When would I use this? Well, I use this when I'm solving systems of linear equations. So if I have more than one line in the plane, I write, or more than one line, then I write them in each of the lines in standard form. The point slope form for the equation of a line. So the point slope form for the equation of a line is just y minus y1 equaling m times x minus x1, where m is the slope of the line, x1, y1 is a point on the line. You can only use this for non-vertical lines since you have to have a slope, and slopes are not defined for vertical lines. When do we use this? Well, basically, this is the form that's always the easiest to use. So this is the form that you will use, except for the cases that I give you, above and below. So except for the special cases that I tell you about, this is the form that is most used. Okay, next, the two-point form for the equation of a line. The two-point form for the equation of a line is just y minus y1 over x minus x1 equaling y2 minus y1 over x2 minus x1, where I'm assuming that x1 is not equal to x2 and that x1, y1, x2, y2 are two distinct points on the line. Again, this can only be done for non-vertical lines. And of course, this is where x1, y1 and x2, y2 are two distinct points on the line. When do I use this? Hardly ever. So only when, I would say hardly ever. When they ask you to do a 2-point form is when you would do it. The symmetric form for the equation of a line. Very similar to it's almost identical to the 2-point form. Just instead of you would call the slope b over a. And so if you do that, then these forms are really the same. Just multiply both sides of your equation or divide both sides of your, multiply both sides of your equation by x minus x1 and divide by y2 minus y1. So the symmetric form for the equation of a line is y minus y1 over b equaling x minus x1 over a, where x1, y1 is a point on the line, and where b over a is the slope of a line. Note that there is a notation here that's understood that if you happen to have that a denominator is 0, then the numerator is also assumed to be 0. Okay. So where a equaling 0 implies is that this is a vertical, and b is equal to not 1, and b is the y1, and the y1 is b. Oh, I see. And where the b is 1. Yes. Sorry. And so, yes. So if a is 0, then it's assumed that x is equal to x1 and that the b here is equal to 1. Okay. You should always reduce b over a to lowest terms in this case for that to be true. When do you use this? This is the preferred form for writing, especially if you do lines in more than one dimension, more than two to write it. A parametric form for the equation line. In this case, just let this equal to t. Let the slope here equal t. And then solve for x and y. So the parametric form for the equation of a line is just x equals at plus x1 and y equals bt plus y1, where x1, y1 is a point on the line, and where t is some parameter, and where b over a is the slope of the line. Okay. Again, where x equaling 0 when the line is vertical. So this is used usually when you write solutions of dependent systems of linear equations. So you'll be asked when we're solving system linear equations to write your answer in this form, in the parametric form. The intercept form for the equation of a line. So x over a plus y over b is equal to 1, where a is the x-intercept of the is the x-coordinate of the x-intercept, and b is the y-coordinate of the y-intercept. This can only, happen when a and b exist and where neither a nor b is equal to 0. So you have to assume that this is for a non-vertical line, for a non-horizontal line, and for lines that do not go through the origin. When do you use this? I use this when I happen to know both the x and y intercepts, and neither the x or y intercepts are 0. the slope-intercept form for the equation of a line. Y equals mx plus b. B is the y-coordinate, the y-intercept. Since I have a slope, I need to know what the slope is in that formula. So this can only be, this only holds for non-vertical lines. When do you use this? Well, you use this when you're trying to determine the slope of a line given by an equation. A vertical line. So the vertical line is just x equals some constant, say a, and a horizontal line is just y equals some constant. So those are the equations of a horizontal and a vertical line. Okay, so let's do some examples. Problem number 32. In problems 32 through 25 through 32, graph the line that contains the point P and has slope M. Okay, so let's do that. And so I start out at 1, 3. Okay. And then, so I should write my slope as rise over run. Oops. Okay. So rise over run. So I have a run of 5. 1, 2, 3, 4, 5. And a rise of -2. So I go down 1. And so this is my line. So I have here a run of 5 and a rise of -2. So I go down 2 units. Okay. That's it, I guess. Yes. Oh, I don't need this page. Okay. Next, parallel lines. So 2 lines in the plane are said to be parallel if they do not intersect at any point on the lines. And so, suppose I have 2 lines, L1 and L2, and suppose they're parallel. And suppose that I do this relative to some coordinate system, x, y. Then 2 lines, L1 and L2, will be parallel to each other if and only if their slopes are equal to each other. Is that this is an if and only if. It means that these are equivalent. Where the understanding is if one side of the equation doesn't exist, then neither the other side. So if one slope is doesn't exist, then the other slope doesn't exist. Meaning, if one is a vertical line, then the other one is also a vertical line. Okay. Perpendicular lines. So, 2 lines, L1 and L2. Oh, and I guess I should say that 2L is denoted by this L1 and this 2 kind of like lines next to each other. That's the mathematical symbol for parallel lines. So just having 2 sort of lines next to each other, like that. Okay. Yes, that is correct. So it's under that sort of strange understanding that that an undefined is equal to an undefined, and so the undefined slope equals the undefined slope, meaning two vertical lines are parallel. Okay, that just simplifies the statement. If you just say, well, assume two lines are two, that this still holds even when it's undefined, because then it just makes it easier. You don't have to say two cases. And that's in general, we're sort of lazy and we just sort of say, well, it still holds even when things aren't defined. Okay, so perpendicular lines. So two lines in the plane are said to be perpendicular if they intersect at right angles. So if two lines intersect at right angles, then we say that they are perpendicular. So, so let's do this relative to some coordinate system. So let M1 be the slope of L1 and M2. Now here, I have to make some weird assumptions. So L1 is perpendicular to L2 if and only if the product of their slopes is -1. This is equivalent to saying that the slope of one line is equal to negative reciprocal of the slope of the other line. If that is true, then these two lines are perpendicular. So you can either say, well, don't assume that these are horizontal or vertical, or you make the assumption that the slope of a vertical line is infinity. 1 over infinity, you assume, is 0. And 1 over 0 is infinity. So if I had the slope of 0, then negative 1 over 0 is infinity. So that means that that a horizontal line is perpendicular to a vertical line. For here, you have to make a weird sort of assumption that 0 times infinity is -1. So if you make that assumption, that definition, then it's an if and only if statement. Okay. There's almost easier to say, don't assume that they're vertical or horizontal, because that weird. Well, it's easier in the case where we have the reciprocals, but when you multiply it, it's not so intuitive. In problems 53 through 78, find an equation for the line with the given properties. Express your answer using either the general form or the slope-intercept form of the equation of the line, whichever you prefer. Problem 74, perpendicular to line, y equaling 2x minus 3 containing the point 1, -2. Okay, so let's do this. So first, let's find the slope of my line, of this line given, of the given line. So the slope of the given line. And so to determine the slope of a line given by an equation, we use the slope-intercept form. So use the slope-intercept form. Y equal mx plus b. Meaning, solve for y. Well, it's already solved for y. So in this case, the slope is 2. The y-intercept is -3, but who cares? I'm only going to be using the slope. So now I want to find the slope of a line perpendicular to the given line. Well, recall that to find the slope of a line perpendicular to another line, you just take its negative reciprocal. So I change the sign and take the reciprocal. And so the negative reciprocal of 2. So now I have a point and a slope. So let's use the point slope form. As I indicated, the point slope form is almost always the easiest form to use to solve problems. Okay, so the point slope form is just y minus y1 equaling mx minus x1. Well, we have the slope, -1/2, and we have the point, okay. Oh, that's just good. Okay, so we have the point 1, -2. And so I have y minus y1 equals m x minus x1. Let me multiply both sides of my equation by 2. And so I get 2y plus 4 equaling -1, because the 2's cancel. Let's multiply the -1 inside, well, -1 x minus 1. Let's multiply the -1 inside the parentheses. So you get 2y plus 4 equals a -x plus 1. Add x to both sides of your equation. Subtract 4 from both sides of your equation. And so I have written my answer in standard form. Wait, they said it in general form. Add 3 to both sides of your equation. Yeah, add 3 to both sides of your equation. So add x to both sides of your equation, subtract 1 from both sides of your equation. And so the general form for the equation of your line is x plus 2y plus 3 equaling 0. Okay, I usually prefer not to write it in the other form, the slope-intercept form, right? Yeah, slope-intercept form. In general, that is more algebraically complex. So I usually don't do that unless I have to. Okay, so let's do the next one. So again, we're going to do the same sort of thing. Recall in problems 53 through 78, find the equation for the line with the given properties. Express your answer using either general form or the slope-intercept form of the equation of a line, whichever you prefer. So this is going to be perpendicular to this line. Well, the slope of a horizontal line, so y equaling 8 is a horizontal line. The slope of a horizontal line is 0. Of its negative reciprocal is undefined. It's infinity or negative. So therefore, Oh, this is perpendicular, right? Therefore, this will be a undefined line, so that's a vertical line. So this will be a vertical line. And so I want to find the equation of a vertical line through the point 3, 4. And so the vertical line is going to have just the value x equaling 3. So that's the equation of your vertical line. Oh, and I guess I want it in, you can't have it in slope-intercept form, so you have to have it in general form. So let's say, let's call this x minus 3 equaling 0. Let's do problem number 83. In problem 79 through 98, find the slope and y-intercept of each line, graph the line. Okay, so it's actually, this is in slope-intercept form. So they've actually given us in a form where you can read off. So in this case, the slope is 1/2. And the y-intercept is 0.2. Okay. So you could just read it off. Next, they want you to just graph this. So let's graph this line. So let's sketch the graph. So I have here, the point is 0.2. And so we have a run of 2 and a rise of -1. And so it should look something like the following. So I have a run of 2 and a rise of -1. No, we don't. Sorry about that. It's the other way around. It's +1. Oops. Okay. So it is +1. Okay, so let me do that instead. 1, 2. I'll just write the rest of these tick marks so it looks nicer. Okay, so I'm here at 0.2, is a y-intercept. I have a run of 2 and a rise of 1. And that is what it should look like. So I have here a run of 2 and a rise of 1. Okay. And that's what it looks like. Okay. Any questions about anything? Huh. Okay. In problems 111 to 114, the equations of two lines are given. Determine whether the lines are parallel, perpendicular, or neither. Okay, so let's do that. So let's find the slope, of the first line. Okay. The computer's giving me a little bit of trouble here. So let's find the slope of the first line. Well, slope of the first line is 1/2. Its y-intercept, not that it probably matters, is -3. The slope of the second line is -2, and the y-intercept is 4. The only reason for determining y-intercepts is just to see if two lines, to differentiate when two lines are parallel and when two lines are coincident. Well, these certainly are not parallel lines. 1/2 is not the same as -2, but their product is -1. One is the negative reciprocal of the other. 1/2 is the negative reciprocal of -2. And so therefore, these two lines are perpendicular. And that is your answer. Okay.